So good evening, everybody, or depending on where you are, good morning or good afternoon. What I'm going to do now is we're going to see other possibilities of making a system evolve, which go beyond the unitary evolution that we have seen so far. And this is going to be very useful for dealing with open systems or take into consideration that a system may become entangled with other systems. So I hope you enjoy and that is productive for you. So we're going to continue our present topic, which is open quantum systems. And what I'm going to talk about in this specific asynchronous lecture is superoperators and non-unitary evolution. And the necessity of us doing this is because we have seen previously that unitary evolution alone does not lead to mixed states or doesn't change the purity of a state. If your state is originally pure, it's going to remain pure. If your state is originally mixed, it's going to remain mixed. But we have seen in nature that sometimes this changes. So there may be other ways of evolving a system that we're going to need to mimic to be able to account for this kind of change. Because we know that unitary evolution alone is not going to do the job. So what can we do? How can we describe this? Because it does happen. We have seen when we talked about mixed states previously that they can arise via two ways. First, we can have classical randomness in the creation of a state. For instance, if your system is embedded in an experiment which is not perfect, you're going to have to find a way of introducing this kind of imperfection. Or if you have some kind of thermal fluctuations, all these kinds of things. And you can have also entanglement with another system. So this is, for instance, when we were discussing these spin up, spin down cases, and we consider two coupled spins, that you realize that the only way to eliminate or to erase the influence of one system was to compute reduced traces and reduced and density matrices, and the reduced state that you would compute in this way was mixed. So this is tricky and we have to address. So one thing that we would like to start with is to see how classical randomness is going to affect the evolution of a quantum system. It's a situation which you can have, and we are in a position to discuss because we know a lot about this density matrix formalism and what in principle you can do. So let's first consider a system that is in a pure state. This is a toy model. So if the system is in a pure state, we know that ρ is going to be given by a single projector, meaning our density operator. Now, we also know that to evolve now, we're considering that we're going to have a set of unitary transformation and we're going to implement some Hamiltonians for a certain time. So we implement a Hamiltonian, we evolve it a bit, and then we change the Hamiltonian. And to change the Hamiltonian, we're going to do this randomly. So you're going to have transformations, which in our case are going to be evolution. And each evolution operator associated with each Hamiltonian Hj is going to be Uj. And we're going to consider this stepwise. So it's going to happen in many, many intervals where J here is going from 1 to n. So evolve a bit, then change the Hamiltonian, evolve again, change the Hamiltonian, evolve again, change the Hamiltonian. So that's what we're going to do. This means that according to what we have already seen previously, that each of these transformations is going to change our state, and in particular, our density operator to uj whole, uj dagger, whereby you evolved a little bit and then you are going to change u. So in total, what we're doing is we're introducing randomness as well, because we are going to choose this unitary transformation that is going to be applied by using a random number generation. So when I was saying, okay, you evolve a bit and then you stop, you evolve again and then you stop, and then you change the Hamiltonian, you're going to change the Hamiltonian using some kind of random number generator. This is a toy model. We're just cooking this up so that you see what possibilities lie beyond when you are trying to evolve a system and going beyond just a single unitary evolution operator. And we're going to have a probability Pj, which is associated with each of these Hamiltonians and these time evolution operators in these J intervals. So if you keep on doing that, after a while you can say that in total, your density operator is going to look like this. It's going to be rho dash, and you're going to have evolved this for many intervals, and it's going to be the sum over j, pj, uj whole, uj dagger, right? You just evolved, changed Hamiltonian, evolved again, changed Hamiltonian, evolved again. We know that each of these operators is a unitary time evolution operator. That's how we define the whole thing. However, because we have introduced classical randomness, the overall evolution is not going to be unitary. And this means that by proceeding this way, a pure state can in principle be transformed into a mixed state. So that's actually what we're looking for when we were saying that these kinds of things may change depending on how we evolve things. And we're going to have to define now something which is going to help us continue with that, namely superoperators. So let's have a look at what an operator is. An operator, or acting on a vector space, is a mathematical object which acts on a vector in that space and returns a vector psi dash in the same space. So this is something we have seen at the very beginning of a course. You have originally some vector psi. You acted with O, which is a generic operator, onto this vector psi, and you generated psi dash. Now, if you would like to define a superoperator, and we're going to note this as here, whatever is your operator, is a mathematical object which transforms an operator to another. So we're going to have rho dash, which is obtained by applying the superoperator S to rho. And if you look, we're going to see that in the model that we have just discussed, which was a toy model, we have done this. We have generated rho dash from rho, whereby both are density operators, by applying these transformations which were randomly assigned depending on the time interval we were taking into consideration. So you are summing over unitary operators, multiplying from the left and from the right, and doing unitary evolutions, but which were assigned randomly, so you ended up with something more general. And because this object was modifying your density operator at the beginning, then you could say that you are having a superoperator. You applied an object, a mathematical object, to an operator rho, and you got rho dash. Okay. Now, this representation here is particularly interesting because this is known as the Kraus representation, okay, with some variations, but every time you can write an operator like this, where you have from the left and from the right this K operator, K dagger, and a sum. This is called the Kraus representation. And all superoperators in quantum mechanics can be written like that. It's a pretty much of a tough statement, but if you remember how things transform, you see that at the end of the day, this is going to work. So this is fairly general. And these Kj, they are linear operators, and they satisfy this property that the sum of Kj, dagger Kj, is equal to the unitary operator and summing over J. And we know these operators Kj as Kraus operators. And in our toy model, if you look where we had this Rho dash equals to sum over J, Pj, Uj, Uj dag applied to Rho, one from the left, other from the right, you see that your Kj would be square root of the probability multiplied by Uj. So you also see that this property that was given here holds, because if you consider then Kj dagger Kj and you sum over it, you find that this is going to be Pj Uj dagger Uj, whereby we know that U is unitary, so this is the identity operator, and you get sum of probabilities, which is going to be 1. So notice that K is not necessarily unitary, but is proportional to a unitary operator. But they do not need to be unitary. And it has several properties. They have properties that are important for us. And we're going to consider also the superoperators, which are written in this form. And properties are that if Rho is Hermitian, has trace 1, and no negative eigenvalues, I mean, this is what you expect from a physical density operator. These three things, if you recall the properties that we have already discussed. Then Rho dash equal as Rho, so this superoperator and the Rho dash that you get from applying a superoperator has to be Hermitian, has to have trace 1, and also cannot have negative eigenvalues. So what we need to prove is that as Rho has first hermiticity, that it has unitary trace, and that it has no negative eigenvalues. So this is what we call complete positivity, and we're going to see this proof next. So to continue our lecture, what I would like to do now is to show that each of these properties holds for the superoperator. So we're going to start with hermiticity. And what we would like to show is that Rho dash, which is superoperator applied to Rho, is equal to Rho dagger dash to Rho dash dagger, which is as Rho dagger. This is what we would like to show. So we're going to start by considering the Kraus decomposition of this. So we're going to write Rho dagger dash or Rho dash dagger as Rho dagger, and we have said that our operator can be decomposed and written using Kraus operator. So we know that we can write this as J sum over J, Kj Rho Kj dagger dagger. Now we're going to use the fact that A, B, C dagger, where A, B, C are operators, is equal to C dagger, B dagger, A dagger. So if we apply this to this guy, we are going to find that sum over J of Kj Rho Kj dagger dagger is equal to j, sum over j, kj dagger, dagger, ho dagger, kj dagger. So we have applied this property here. Now we know that this, specifically kj dagger is going to be kj, because if you take the conjugate of the same operator, you get of the conjugate, you go back to the previous operator, to the original one. And we know also that ho dagger is equal to ho, because we know that ho is Hermitian. This means that the expression that we had above can be written as ho dagger equal to sum over j, kj ho kj dagger, which is actually as ho. From here we conclude that superoperator applied to ho is equal to superoperator applied to ho dagger, so that ho dash is equal to ho dash dagger, which guarantees that this operator, once it was transformed, remained Hermitian. Okay, now we would like to see and prove that the trace is preserved upon the application of the superoperator. So let's look at trace being preserved. And to start with, we're going to consider the trace of ho dash using again the Kraus decomposition. So we have trace sum over j, kj ho kj dagger. Now we can use cyclic invariance of trace, and we can use also linearity of the trace. So we're going to write this, since trace is linear, like this. So just to illustrate, we use here linearity. And to use cyclic invariance, remember that if I do some cyclic permutations in these operators, I'm actually pretty safe. So if I have, for instance, trace ABC, I can say that this is trace CAB. Okay, so if I call this guy A, this B, this C, I can say that my trace of ho dash is equal to sum of a trace of kj dagger, kj ho, which once more can also be written as the trace of the sum over j, kj dagger, kj ho, but we have seen that this is equal to the identity operator from our previous definition. Therefore, I can say that trace ho dagger is equal to trace ho, which proves once more that the trace remains invariant upon us applying this superoperator. Now, we would like also to verify that this superoperator is linear, so we're going to check linearity. And to do that, what we need to do is we're going to apply the superoperator to A whole 1 plus B whole 2, whereby whole 1, whole 2 are density operators. And A and B are complex numbers. So once we apply this, we're going to get that this is going to be using, again, Kraus decomposition, Kj, A whole 1 plus B whole 2, Kj dagger, whereby this can also be written as sum over j, Kj, A Kj whole 1, Kj dagger, plus B Kj whole 2, Kj dagger. And this also can be written as A sum over j, Kj whole 1, Kj dagger, plus B sum over j, Kj whole 2, Kj dagger, which verifies that this is linear, because this means that I can say that this is a superoperator of whole 1 plus B superoperator superoperator of whole 2, and this is equal to superoperator applied at A whole 1 plus B whole 2. So linearity is verified. Now we need to talk about positivity as well, because we said, okay, you always have to be sure that your eigenvalues are going to remain positive, all of them. And Rho, as a density matrix and as a density operator, has positive eigenvalues because they are associated with probabilities. So the next thing that we would like to prove is positivity, meaning if you consider an operator, which in our case is going to be Rho, S of this operator maps positive operators to positive operators. Okay, so let's have a look. For instance, let us consider an operator A, which could be our density matrix, but we're making it a bit more general. For instance, the operator A with only non-negative eigenvalues. Not all of them are 0, but we have with only non-negative eigenvalues. And not all of them are 0. So just to rule out the trivial solution. So if we consider this, we can write the spectral decomposition of this operator, which actually we have seen how it looks. It looks like a sum of projector. So we can say that A is sum over I, lambda I. So these are the eigenvalues, which we have seen are non-negative, and these are projectors onto eigenvectors. We can always do this. And if you think about it, this would be the case for a density matrix, because we know that the density matrix of a system or density operator always has eigenvalues associated with probabilities. And that's pretty much what we're interested in here. So we would like to show that superoperator applied to A is bigger than 0, meaning the eigenvalues are going to remain non-negative. So to show that the mapping we are interested in is positive, it is sufficient to show that nu as a nu, whereby we are considering here two states, is bigger or equal to 0, which means lambda I are non-negative. Okay, so let's go for it. And let's consider once more Kraus decomposition, and let's take these other state vectors defined like this. So expectation values of the transformed operator have to be non-zero, because if this happens, then we know that the eigenvalues are non-negative, or is bigger than 0, bigger or at most equal to 0. So we consider this, and we're going to write again that this expectation value of SA is going to be equal to sum over alpha U K alpha A K alpha dagger U, and we have defined this guy. So we know that this is going to be omega alpha, and this is going to be the corresponding bra. Now we know how we can write this operator. We can write this as a spectral decomposition. So we're going to insert spectral decomposition of A, and this is going to give me then, making a bit more space here, that nu as superoperator of A, nu is going to be sum over alpha and I, lambda I, omega alpha is defined above, I, omega alpha, and if you multiply this is going to be the modulo square of omega alpha I of this inner product. We know that if you put this together, by construction, this has to be non-negative, so this is bigger or equal to 0. And we also know that the modulo square of whatever you're computing, whatever norm you're computing, has to be bigger or equal to 0, which tells you that S applied to A is bigger or equal to 0. So we can guarantee that the mapping that you are doing is positive. So now, just to close, let's make a few observations. First, this Kraus operator sum representation, which we have defined, has to be positive, Hermitian, and trace preserving. However, not every superoperator satisfying these three properties, namely hermiticity, positivity, and trace preserving, has a Kraus operator sum representation. So far, we have been lucky because we consider density matrices, and this is pretty much the case with density operators. But you have to be careful when you have transformations dealing with compound systems and subsystems of compound systems. And that's why we need to strengthen positivity, and we need to talk about complete positivity. And what we mean by that? We mean that for a transformation to be physical, it must transform whole to a physical state, even if it's only acting on a subsystem. Because sometimes what happens is that you have two subsystems, for instance, A and B, and you have superoperators in which you transform a reduced state and you get always positive eigenvalues or non-negative eigenvalues, could be vanishing as well. But the superoperator acting on the full state may have negative eigenvalues, which means that you are transforming and everything is okay into a subsystem, but this positivity condition is not fulfilled for the whole system. So that's when you need to be really careful. For instance, we're going to see some example in the synchronous lecture related to transposition, and we're going to see that sometimes these things don't work. And just to conclude, any superoperator that is Hermitian, trace preserving, and completely positive, in the sense of the complete positivity that we have talked about, can be written in the Kraus operator sum representation form, which is this form which we have discussed. So this is an important point, and we're going to use all these properties subsequently when we talk about the evolution of open quantum systems. So with this, we concluded this clip. I hope you keep on following, and we're going to have more details about the evolution of open quantum systems in the 9th asynchronous lecture and a bit in the synchronous lecture 2. So keep on watching and see you soon.